Okay, so the first manufacturing processes that we're going to look at are casting and molding. This is section 2 in your textbook, the first chapter of which is chapter 4, which is going to cover the basics of the casting and molding process, both the metal processes and the plastic or polymer processes. Okay, so let's jump in. And the first thing I want to look at is kind of to give you a sense of the volume of casting worldwide, is to look at the latest data that I have in terms of the volume or the metric tons of casting that are done across the world. Now, keep in mind this is metal casting, and there's actually more plastic casting or molding being done around the world. But metal casting is one of the most prevalent and historic manufacturing processes that man has ever known, dating back from the earlier times all the way through the different industrial revolutions to now. So you can see in this, these are 2019 numbers. You can see that China is the world leader in metal casting production, which probably shouldn't be a surprise. Almost 50%, 44.5% of the world production of metal casting is done in China, which equates to nearly 49 million metric tons. Okay, Europe comes in second at a little over 13 million metric tons. And keep in mind, when we're talking about Europe, we're talking about the EU here. Okay, so I'm not talking about the other, smaller countries that are outside the EU. These are EU countries. So this is 13 million metric tons, which is a little, almost 12%. India comes in third at 11.5 million metric tons, which is about 10.5%. And then the U.S. comes in, which is slightly below. Again, this is 2019 numbers, slightly below India at 11.3 million metric tons, or a little over 10% of the world production. And you can see the other countries here and their representation. In 2019, there were 109,529,364 metric tons of metal cast. All right. If we break it down by the type of metal casting that we're looking at, what's interesting is, and maybe it's not a surprise, again, iron alloys, right, which basically we're talking about cast irons and steels, by far are the most cast metals. That is, gray cast iron is the largest percentage, with again nearly 50%, 48.1%, at 51 million metric tons. Ductile and malleable iron come in after that with 23.6 million and not quite a million for malleable or white iron. And then we have steel production. Steel production is still less than half of the nodular iron, right? A fifth of the gray iron, but it's still substantial, 10 million metric tons. Then after that, what may be surprising to you is aluminum. Actually, there's more aluminum production than there is steel. All right. And this is typically because the aluminum production, aluminum casting is going to be for smaller objects, right? Steel is going to be mainly for building materials. But aluminum is going to be for smaller objects, so there's going to be more aluminum production. It's also easier to cast, right? It doesn't require the substantial infrastructure and equipment that the steel does. And then the other types of alloys or materials, metal again, that are cast, we have copper, zinc, magnesium, and then other non-ferrous. All right, and so you can see a breakdown right here. Again, gray iron is about 50%, ductile iron is almost a quarter, and aluminum is 16%. All right, so again, these are 2019 numbers, but just to give you a sense of the production. If we break it down further and focus more on the U.S., there's not really a shift here, right? So from the world totals to the USA totals, there's not a shift in terms of the order here, right? Aluminum alloys still are more than steel, right? Gray cast iron is still the highest. Nodular comes in second. All right. And then we have malleable. So if I do like a little back and forth, you can see that the names don't change in order. So these are in order from largest to smallest, and they don't really change here. I did notice that copper alloys and zinc does change, right? Zinc is at 330, copper is at 319. So that's my bad. That was a little bit of a typo on my part. So you can see there is a slight change here between copper and zinc. That might have to do with the natural resources that we have. Other countries, and if you can see here, we have a quite substantially higher, almost 1.9 million metric tons of copper. And that might be that other countries have larger reserves of copper as a natural resource than the U.S. And so that's why it's not really done here. All right. So moving on to the casting industry, how do we start to classify the different casting processes? And there's a couple of different ways we can classify it. This is according to your textbook. So in the textbook, we can classify it by the types of molds, whether they're expendable or permanent. And actually, this is how your textbook classifies it. If you look at the different chapters that are covered in this in this section, casting and molding. We have expendable molds, that is molds that are broken apart and they're only used once, and then permanent molds. And permanent molds, obviously, as the name says, they're going to be reused over and over again until they just wear out. Types of activities, we have smaller independent shops, and then we have shops that are going to be doing just casting. Types of material, metal, plastic, and ceramic. There's some ceramic done, casting done, and you might think of plates and dinnerware and things like that. Those are cast. Cups, ceramic cups. But for the most part, metal and plastic is where we're going to focus on the types of material. And then we can also classify it by the steps that are taken. And these steps are, pretty straightforward. How to produce a casting? Well, first we need to prepare the mold. Then we need to prepare the casting material, that is the metal or the plastic. Then we have to get the material, in this case in molten form, into the mold. So we introduce the material into the mold. Then we allow the material to solidify, and this means that it's cooling, okay? And then we extract the cast object. Okay, so these are your typical 5 steps. Not every type of casting operation follows exactly these 5 steps. Okay, especially for permanent molds, we don't have to prepare the mold every time; it's already prepared, and so on. But we'll go through each one of these a little bit more in detail. So what kind of advantages and disadvantages do we have in the casting and molding manufacturing processes? Well, the advantages are we have a great deal of form freedom. That when we talk about form freedom, what that means is we're able to cast shapes that are designers' design, right? We're not limited in what we can design by the manufacturing processes. So we have good form freedom. It's not unlimited, but we do have good form freedom with casting. We have good material properties, not great, as you'll see, not as good as forging, where we get much stronger materials, but still good material properties. And the parts retain their strength at elevated temperatures. So a cast part, if it's used in a high temperature kind of environment, it's going to retain that strength at the higher temperatures, at the elevated temperatures. What are some challenges that casting has? Well, it's a very low volume production process, especially the expendable molds, like they're doing in this picture over here. This is a sand casting operation here. having to prepare the mold every time, having to break the mold apart to get to the part, this greatly slows down the casting process. So low volume, we just can't do a high volume casting. We have long cycle time. Cycle time is the time it takes from the start of the casting process or the start of the manufacturing process until you're done with the manufacturing, until you have the part in your hand. And because of the cooling that needs to be done before you can extract the part, a casting operation has a lower cycle time, a longer cycle time than other operations. We cannot control tolerances very, very well. Oftentimes that means that the cast part has to be machined in the secondary operations. We have poor surface finish, right? You can imagine a sand casting is going to have a surface finish due to the sand that is going to be very rough. And then material properties are not that great. And again, this goes back to the comparison between a forged part or a forging, where we have much higher material properties. Even machining has higher material properties than casting. Castings can be quite brittle if you're not careful. So they have to be used in certain, they can only be used in certain types of applications. All right, so let's look at the different casting metals, right? So common casting metals are iron, aluminum alloys, magnesium alloys, copper alloys, tin, and zinc. Okay. Notice that steel is left off here. Okay. Steel is left off here. We'll talk about that later, but this is an example of a large sand casting. This is over 1,500 pounds, quite a large piece here. Iron we can break down further into four main types of iron. We have gray cast iron, ductile or nodular iron, white cast iron, and malleable iron. Each one of these have different material properties, and so that's why we have a breakdown in the different irons. All right. So looking at the breakdown of these, gray cast iron is very corrosion resistant. It has a high temperature resistance, but it has very poor ductility. What that basically means is when you bend it or when you try to bend it, it's just going to shatter or break. Okay. It's not very flexible. I know it's difficult to imagine a metal being flexible, but you can. I'm sure you can realize that aluminum. If you take a piece of aluminum and bend it, it has high ductility. All right. Ductility plays an important role because we want our metal parts to be to not shatter when they are used, right? And so gray cast iron is not going to be an option there. How do we make gray cast iron? Well, this is the most common type of cast iron, and the alloy itself is 95% iron, basically between 2 and 4% carbon, and a little bit of silicon. This is the sand, 1 to 3% silicon. The name is derived from the grayish color that it has, right? That's why it's called gray cast iron. White iron has high temperature resistance again. It has high strength, right? But again, it has poor ductility. So here we're trying to achieve white iron in its difference from gray cast iron basically adds a strength bonus, right? So white iron has a higher strength. How do we make white iron? Well, when we take iron and we cool it rapidly, what that does is it locks in the carbon into the iron matrix. Okay, so gray or ductile iron can be chilled to produce a surface of white iron. So oftentimes what happens is you have a gray iron part, right? A part that's made from normal iron, a gray iron, but when you chill it, when you cool it rapidly, the surface is going to cool quicker, right? Because it's on the outside. And what that is going to do is basically create a protective shell of white iron around the gray iron core. And so the benefit here is we have a high strength surface surrounding the gray iron. And that's how white iron is used. Ductile or nodular iron, this has high ductility. So here's the key here. This was an invented type of iron, right? It was invented, I think, in the early 1900s. Maybe you can look up the year that it was invented. But it was invented and in order to solve the low ductility problem that gray iron has, right? So it has higher ductility. I shouldn't say it has super high. It's not in the order of steel or aluminum, things like that. How is ductile iron created, or nodular iron? Well, the iron is treated with magnesium before it's cast, and that magnesium basically facilitates the formation of carbon into spherical shapes. That's why it's called nodular iron, nodules or spheres, instead of flakes. So gray iron, the carbon, during the processing, as it solidifies, the carbon is going to form flakes, right? And the flakes make it so that it has poor ductility. When we change those flakes by the addition of magnesium into nodules or spheres, that basically gives the iron matrix more ductility. Okay, so that's ductile iron, and then we have malleable iron, and malleable iron is basically white iron that has been further heat treated. Heat treating basically means that we're going to take white iron and we're going to heat it back up to around 1600, almost 1700 degrees Fahrenheit, and then allow it to cool slowly. All right. So those are some of your casting metals. So let's see how the casting process is done. Okay. There's two main types of casting processes, right? And here we're talking about pouring a liquid metal into a mold. And so the two main types here, we have a top-down process, right? So we're pouring the liquid metal in here, and you can see the liquid metal comes in through the top, and it fills up from the bottom up, okay? And then we have the bottom-up method. So we're pouring in the liquid metal, and it's going to fill a reservoir, and then it's slowly going to fill in from the bottom up. So this is a bottom-up method and a top-down method. All right. Both of them have their benefits and negative aspects of it. And we're going to look at that in a second. The bottom up filling reduces splashing and any trapped air bubbles, right? Bottoms up. But the splashing, what the splashing does, why we want to get rid of that, is splashing increases the liquid surface area. You can imagine that when a liquid is splashing, all those little bubbles that are formed, all those splashes are going to increase the surface area around that part. Surface area in iron is going to allow oxidation. Oxidation is a fancy word for rusting. And believe it or not, the rusting happens that fast, and rust is bad. So we don't want rusting, we don't want oxidation to occur. And so increasing the surface area is going to increase the oxidation, which is bad. So as I said, oxidation negatively affects the material properties. So it can affect, for example, ductility. That means oxidation can make a part less ductile. So one of the things that you're going to see over and over again, especially with casting and forging, is the eutectic diagram. This is called a eutectic diagram, and basically it's a diagram of what happens as a metal cools. Okay, so on the vertical axis here we have the temperature. This is the temperature of the metal as it cools, right? And across the bottom, the x-axis is basically showing you the different alloying percentages. Okay, so over here on the left, we can have 100% of a material A. Over here on the right, we have 100% of material B. And somewhere in the middle, we have percentages of the alloy of A and B. So for example, let's talk about iron. Iron is basically, cast iron is basically iron plus a little bit of carbon. So we can say the iron is going to be the B element, and the carbon is going to be the A element, and carbon is, it's going to be somewhere over here with a very small percentage of the carbon and a higher percentage the iron, right? And then what you do when you identify that, and we'll go back to this, this percent of A and B, you can predict how the material is going to solidify. So, we start up here with a material that has this composition. So imagine a vertical line going straight up at a high temperature. This is all liquid. And as the part cools, it's going to directly drop down through these different regions. And these different regions identify where we have different parts of that metal solidifying out, right? The L basically indicates liquid, and then the alphas and betas indicate the solidifying component here. All right. So, and we'll talk about this more. I know that was kind of a quickie glance at it, but we'll talk about that more. So low viscosity metals will fill the mold details much better, right? Low viscosity, think of syrup, right? So if we're filling a mold with syrup, right? The syrup, because it's moving in slowly, is going to fill all the little nooks and crannies very well. So we want that, right? But the downside to low viscosity is, well, it fills slowly, right? And what happens when a molten metal is filling slowly? Well, it's going to start to solidify because it's so slow. So alloying elements always lower the viscosity. So the percent of alloying elements are going to help lower the viscosity. Steel has 0.2% to 0.6% carbon, so therefore it has a high viscosity, relatively speaking. Cast iron has 2 to 4% carbon, so it has a low viscosity, right? More carbon indicates lower viscosity, more syrupy. Alloying elements reduce the melting temperature, right? So that the more alloying elements that we have, the easier it is to melt. It melts at maybe 1,000 degrees versus 2,000 degrees as a pure metal. So the eutectic composition is the composition of the metal plus the alloying elements, resulting in the minimum melting temperature. So the eutectic composition right here, this represents the minimum melting temperature. Remember, L represents entirely liquid. Everything is liquid. So there is a point in every material eutectic diagram, a perfect percentage of alloying elements and base metal where it meets right at this intersection. That point, notice that point is the lowest temperature where everything is going to be liquid, right? If the temperature is any lower, we're going to have some solids in there. All right. So that's called the eutectic temperature, that temperature. And the eutectic composition is the ideal alloying percentage with our base metal. And this point is called the eutectic point. All right. So let's look at an example here, right? I said we'd look at an example. So we're going to look at the iron-carbon phase diagram. So this is a typical phase diagram for iron and carbon, right? And you can see here we have 0% iron. And here we have the cast iron range is right in here. And in this example, we're going to look at a 4.3% carbon, right? So this is 4.3% carbon. And we go up here and you can see the eutectic point right there. And eutectic temperature is just a shade above 2,000 degrees Fahrenheit, right? It's actually 2,066 degrees Fahrenheit. Above that, for 4.3% carbon cast iron, you're going to get entirely liquid. And then as this 4.3% carbon solidifies, it's going to travel straight down, or as it cools, I should say. As the temperature drops from 2,000 down to, let's say, 1,600, now we're going to have some solid elements. As it moves down here, we're going to have to 1333 Fahrenheit. We're going to have more solid elements precipitating out until it cools down to 0. Okay. So the molten metal fluidity increases around the eutectic point. That means it flows better. Lower melting temperature reduces energy costs and increases throughput, right? What that basically means is you're heating it up less to still get it to liquid. So this is good, right? This is good for manufacturing, lower melting temperature. Castings have higher alloy content than wrought alloys. Wrought alloys are basically the forging alloys, right? Higher alloy content reduces material properties, though. So the more carbon we get into it, the worse the toughness, ductility, and fatigue strength. So there's a trade-off here, right? There's a trade-off. So let's look at some of the compositions of the different irons. I won't go into much of this. You can read this on the in the PowerPoint and in the textbook. But for example, gray cast iron, 3.4% carbon, 1.8% silicon, 0.5% manganese. Right, cast. It has a tensile strength of 50 KSIs. The elongation percent is 0.5 inches per 2 inches, 0.5 inches of stretch, per 5% stretch inches per 2 inches. And then the Brinell hardness is 260, right? And then you can compare all of these, right? So the yield strength isn't given on this, but you can see malleable iron and ductile iron. The yield strength for the ductile iron is much higher than the malleable iron. Remember, malleable iron is going to be gray cast iron or white cast iron, and then it's allowed to anneal, or it's reheated and then cooled again. All right, so that just gives you an idea. So let's talk about filling the mold. So we'll focus on filling the mold here with the flow of the liquid metal. All right, so high-speed filling. Right, we're pouring it in. Maybe this is a top-down approach. We're pouring it in. The mold fills quickly, right? We get more turbulent flow. That is, there's more splashing. Therefore, we get increased oxidation. This is how the turbulent flow is. These are little splashes, right? You can imagine splashes. And therefore, we get reduced material properties. So we fill it quickly, but we get worse properties, all right? So this surrounding zone right here, this is kind of your oxidation zone. That's your oxidation layer. And so when it's splashing, we get more oxidation. When we have a slower filling speed, right? Higher viscosity, maybe, where it flows in nice and gently. Notice the oxide layer is much less, right? Less here. We only get this kind of oxide layer. So we get good casting quality. But because we're slowing it, the filling down, the solidification may occur prematurely. That is to say, while it's filling up, some of it may start to solidify, which is definitely not good. Laminar flow is basically the term that we use for, it's the opposite of turbulent flow. Laminar flow is basically very smooth flow. We get no oxidation or very little oxidation, and therefore we get improved material properties. Again, I want you to understand that there's trade-offs. That's the main thing that you want to understand. So what are these trade-offs? Well, flow begins laminar, but after critical flow length, it turns turbulent. All right. Now, this is important to understand. And unfortunately, we're in the winter, so it's hard to do this. But if you go out with a hose, a water hose, and you turn it on, there's going to be a period where the flow is going to be laminar or smooth. And then after a certain point of the water running, it's going to turn turbulent, right? And so this happens after what's called the critical flow length. And we can actually calculate what the critical flow length is. We're not going to in this class, but you can calculate. Some other trade-offs. Thin-walled castings must be filled quickly. Now, this makes sense because a thin wall is going to solidify quicker than a thick wall or a thick part, right? A thin wall is going to have less, it's going to allow heat to dissipate more quickly. Therefore, it's going to be, it's going to cool and solidify quicker. So we must fill them very quickly. If we fill them slowly, they're going to solidify prematurely, and then we're not going to get a good part. We want to use gates and runners to fill the areas of the mold. And so here we have an example of the gates and runners. Here's the part, right? Here's where we pour the liquid metal in. So you can imagine the liquid metal is going to pour in here, and then it's going to go around here, and then around the runners and into the gate. The way I like to imagine this is, think of this as a theater filling up for a play or some kind of a concert, right? So here's where the people come in to the theater, and then here's the hallways that people go around to get access to the doors into the theater. Gates require additional finishing and after casting, right? So after the casting, all of this is going to be solid. And so then it's going to slow down the processing. Why? Well, because we have to take this part out and we have to send it to the machine shop so that they can cut off the gates and the runners. So the less gates and runners, the quicker the processing time can be. But the downside is the less gates and runners, the harder it is to fill the mold so the part is properly solidified. Again, thinking back to a theater, if we only come in through one entrance, it's going to take a long time for the theater to fill because everybody's going to, want to sit down here, and they may not want to go all the way to the front. All right. Here, this allows entryway to the front of the theater. All right, so before we begin the next section, that's been about 30 minutes, so I'm going to cut this off here. We'll pick up with this solidification process on the next part of this presentation. We're about halfway through the presentation too, so this is perfect timing. All right, I'll see you in the next video.